This is a course on engineering mechanics. In which we would be studying interaction or let me be more precise, mechanical interaction between different bodies when they interact through the forces applied on each other. This would consist of two parts, statics and dynamics. In statics, we would mainly be concerned with equilibrium between different bodies. I would specify later what we mean by equilibrium. And in dynamics, we would be concerned with how different bodies move under the influence of different forces they apply on each other or when the force is applied from outside. In the first part, we are going to focus on statics, which is the study of equilibrium between different bodies. So, of equilibrium between bodies. When we say equilibrium, in general it means that there is no acceleration on any part of the system. In statics, we will specifically be concerned with when all the subsystems, all the systems or subsystems are not only not accelerating, but are static. That is, they are not moving. The study of statics or dynamics is based on Newton's 3 laws. Of motion. So, let us start by their description. The first law states that a body does not change its state of motion unless acted upon by a force. So, if a body is moving in a straight line, it will keep moving in that straight line until a force is applied. Similarly, if a body is static, is sitting somewhere, unless a force is applied, it will not start moving spontaneously. The first law is based on observation, and it is part definition. You may ask, definition of what? It gives you the definition of an inertial frame, and we do most of our calculations in an inertial frame. An inertial frame by definition then is the one in which the body does not change its state of motion unless a force is applied. For example, in this room, for all practical purposes, this room is a good inertial frame, because if I see somebody or some body somewhere, it is not going to change its state of motion without a force being applied to it. On the other hand, suppose I am on a train which suddenly starts moving. As soon as it starts moving, you see objects outside which are accelerating in the opposite direction by the same acceleration. So, without any apparent force. So, that accelerating train is not a good inertial frame, is not an inertial frame at all. Then there is second law that states that force applied on a body is proportional to the acceleration that it produces. Then we write F equals m a, which defines for us the mass as well as the force. So, this is also based on observation and part definition. It defines for us something called the inertial mass. Suppose I take a standard body, apply a force on it and produce an acceleration a1. So, that F equals m1 a1, and I take another body, apply the same force on it, maybe by a spring, maybe by hitting it or something, and find that acceleration is a2. Then the mass of the second body is going to be m1 times a1 over a2. This becomes the operational definition of inertial mass. So, this is part definition. Then it also tells us, given a mass, I can also measure the force in newtons as m times a. Mind you, this is operational definition. I cannot always use it though, because suppose I am pushing a wall, the wall does not accelerate. So, I cannot really determine its mass by measuring the acceleration when I am pushing it. Then there is Newton's third law that states that for an action there is always a reaction. That means, if there is a body A, it is pushing another body B by a force F, then there is going to be reaction on A by B in the opposite direction. A very confusing situation arises in this when most of the students ask, if the forces are in opposite directions, why don't they cancel each other? They do not, because you see force A is applying a force on B, it produces something on B. On the other hand, A is being pushed by a force by B in the opposite direction. So, it is acting on a different body, therefore, they do not cancel. However, if I take the entire system as one, then they being internal forces, they do cancel, but be very careful in applying it. Having given these preliminary discussion of Newton's laws, of which we will mostly be using the third law in the statics part and will be using the second and third law in the dynamics part. Let us now start with a review of vectors, because we will be using vectors extensively to represent forces, velocities and things like those. So, it is a good way to start this course by reviewing what we know about vectors. I am sure most of you have learnt about it in your 12th grade, but we will now make it slightly more sophisticated. Why do we need vectors? It is because there are certain quantities which have magnitude as well as a direction. For example, if somebody tells you that I am pushing a box by a force of 10 newtons, it does not convey the full meaning until I say that I am pushing it to the right, to the left, in this direction or in this direction. Until a direction is specified, the complete description is not there. So, to specify a force, I need both its magnitude as well as its direction. Similarly, suppose somebody comes and asks you, where is your friend's house? And you say it is 500 meters from here. Again, it will be a meaningless statement unless you tell him that it is 500 meters to the east, to the west, to the north, to the south, southeast. So, a plus a direction is also needed. So, there are certain quantities for which you need the magnitude as well as the direction, and these quantities we are going to call vectors. Having defined vectors, how do we represent them? Let us ask that question. There are two ways, one is graphical and one is algebraic. We will first do graphical method and see that it gets little complicated when we go into many vectors and do many operations. Then we will do a algebraic way of writing vectors. So, graphical method of representing a vector is that you make an arrow with the arrow showing the direction and the length of the arrow showing the magnitude of the vector. In this manner, if we now have two vectors, how do we decide whether the two vectors are equal or not? If there are two vectors given, they will be equal if they produce the same effect. So, their direction and magnitude must be the same. Graphically, that means that if there is a vector A, another vector which is parallel to it and has the same magnitude, B is equal to A. So, I can have a vector parallelly shifted compared to A, but still it can be equal to A. So, in this case A is equal to B, because both of them have the same direction and the same magnitude. On the other hand, if I make a vector here C, its magnitude may be the same as A, but it is not. It does not have the same direction as A, and therefore, A is not equal to C. One has to be very careful in the effect of equal vectors. Two vectors being equal does not mean that their effect will always be the same. For example, if I take a wheel, I apply a force on its top, say 10 newtons. If I apply the same force on the axle in the same direction, although the two vectors are equal, their effect would not be the same. In the first case, the wheel will start rolling. In the second case, it will just move forward without rolling. So, although the vectors are equal, their effect is not the same. On the other hand, think of the same wheel, if there is a rope pulling it which is tied to its end, whether I apply a force here, here or here along the line of action, its effect would be the same. I can also hit the disc from this side by the same force, and that would also produce the same effect. So, equality of vector has to be further specified by something else, and that is, if there is a vector and no matter where I apply it along the line of its application, if the effect is the same, then it is known as transmissible vector. So, not only equal, but if I can apply it at any point along the line of its action and it produces the same effect, then it is transmissible vector. For example, force is a transmissible vector. So, force has this quality called the transmissibility. Okay. Having talked about equality of vectors and transmissibility of vectors, let us now see how do we add and subtract vectors using our graphical method. This is more or less a review, because I am sure you have learned this in your 12th grade. So, if I want to add two vectors A and B, what we do is, so we are doing A plus B, what we do is take A, on its head put the tail of B, and then draw a vector starting from the tail of A to the head of B, and that gives you A plus B. You may ask, why do I add this way? Does it make sense? It certainly does. Suppose there is a ball moving like this with velocity v1, and I hit it so that it acquires a velocity v2 in this direction. Experience tells me that it would be moving in a direction like this, which would be a sum of v1 plus v2. You see, I have added v1 and v2 using the prescription I just gave you. I draw v1 and put the tail of v2 at on the head of v1, draw this vector, and this gives me v1 plus v2. So, this is how we define the addition, or we obtain the addition of two vectors. It is also easy to see that addition of vectors is commutative. That is, A plus B is same as B plus A. Let us see that. So, let there be a vector A and let there be a vector B, then this is A plus B. On the other hand, if I draw the vector A with its tail at the head of B, then this would give me B plus A. But this arm is parallel to this, because this is a parallelogram. So, these two vectors are parallel, and because this is a parallelogram, this magnitude is the same as this, and this implies A plus B is the same as B plus A. So, summation of two vectors is commutative. You see, graphical method is giving you a very visual way of looking at vectors. Next, we can use addition of vectors to define the product of a number and vector. For example, if I take A and add A to it, you can easily see that the length becomes doubles, and therefore, its magnitude is 2A, and since it is the same direction as A, I can write this as 2 times A vector. Similarly, if I add 3 vectors, the magnitude would become 3 times A, and it is in the same direction as A, therefore, I can write this as 3A. So, this defines the multiplication of a number with the vector. It is nothing but adding that vector that many times. How about 1.5A? 1.5A would be A plus half the magnitude, but in the same direction. So, this would be A, this would be 0.5A, and their addition gives me 1.5A. Can I multiply a vector by a negative number? The answer is yes. So, product of a negative number and a vector. Recall from your school days, what does multiplying by a negative number mean? If I go to number line, this is 1, 2, 3, 4, minus 1 is in the other direction, minus 2 is also in the other direction, minus 3 is in the other direction, and so on. If I multiply minus 3 by minus 1, it becomes 3. So, minus 1 times minus 3 becomes 3. What the multiplication by a negative number is doing, therefore, is changing the direction. Similarly, if I take negative a, which will be minus 1 times a, this would be nothing but changing the direction of a. So, if a is this, minus a would be pointing in the other direction. That is the meaning of multiplying by a negative number. Of course, once you define multiplication by minus 1, you can define multiplication by minus any number. You just make it that many times more. Having obtained minus a, it is now very straightforward to subtract vectors. So, how do we do subtraction of vectors? Suppose I have to subtract b from a. This would be same as a plus minus 1 times b. So, what do? We take vector a and I want to subtract b from it. This would be the same as taking a and adding minus b to it. So, a minus b would be a minus b would be this. This would give me a minus b. And you can see right away that a minus b is not same as b minus a, because b minus a would be b minus a. Minus a would be opposite to a, and therefore, this would be like this. This is b minus a. So, you can see that a minus b is not the same as b minus a, but through graph you can see very easily that a minus b is equal to minus of b minus a. So, what we have done is addition and subtraction of two vectors. Similarly, if you have to add 3 vectors, you can do a plus b, then add the third one to it. If you have to do 4 vectors, you can do a plus b, c plus d, add the 2 resultants again, and so on. Let us do 2 examples showing the summation of 2 vectors and subtraction of 1 vector from the other. So, example 1, suppose there is a person who walks 300 meters to the east and then 400 meters to the north. We want to ask what is the total distance he covered. This is obviously 700 meters, and then we ask what is the vector displacement which is a vector quantity of the person from the original position. To get that, we have to add the 2 displacements vectorially. So, suppose the person started from here, he moved 1, 2 and 300 meters to the east, and then 1, 2, 3, 400 meters to the north. So, this is his first displacement up to this point, and then second displacement from here to here, and therefore, the net displacement would be in this direction. This is 400, this is 300, and therefore, this would be 500. So, net displacement of the person is 500 meters, and in which direction? At an angle theta, where theta is going to be tangent inverse of 4/3 from the east towards north. So, this is his net displacement. This is how you would find the addition of two vectors, and which gives you the magnitude and its direction. In the second example, let us take the case of two persons pushing a box so that the net force F net is, let us say, 12 newtons to the right or to the east. One person applies a force F 1, which is 5 newtons to the north. We ask what is the force applied by the second person. Let it be F 2. Then we know that F net is going to be equal to F 1 plus F 2, and therefore, F 2 is equal to F net minus F 1. F 2 is equal to F net minus F 1. We have been given that F net is 12 newtons to the east. F 1, this is F net. F 1 is 5 newtons to the north, and therefore, F net minus F 1 is going to be, this is F net minus F 1 will make going to the south, and this would give me F 2. You can see that F 2 is going to be 13 newtons, because this is 12, this is 5. At an angle theta equals tangent inverse 5/12 towards south from the east. So, I have given you two examples, one in which we added two vectors and one in which we subtracted one vector from the other. Next, we ask, can we define product of two vectors? The answer is yes, but before doing that, I will take a slight digression, and now we will go into vector algebra, representing them by numbers and in a different way algebraically. So, first let us represent vectors in an algebraic way, and then we will be able to define the product of two vectors properly. Not only that, representing vectors in an algebraic way would make addition and subtraction of two vectors easy when we have many vectors. So, for that, first I introduce the concept of unit vector. A unit vector is a vector of magnitude 1. So, let us say unit vector n, and to show that it is a unit vector, we make a hat on top of the vector. This magnitude is going to be 1, and it could be any direction representing the vector in that particular direction. In particular, now we will take the x, y and z axis, Cartesian coordinate system and define unit vectors in x direction, call it I, unit vector in y direction, call it j, and unit vector in the z direction, call it k. Now, any vector can be written as a, what I call the x component of this vector, times I plus a the y component of this vector j plus a z and z component of this vector k. So, this is known as the z component, y component, x component. You can see that what we are doing is multiplying this unit vector by a x. So, this will give me a x times this, a vector in this direction, let us say this a x I, and I add this to a y j. So, I will draw it parallelly here. This will give me a x I plus a y j, and on top of it we will add say a z k. I move it here parallelly. So, the net vector A would be something like this. This is a z k. Although in this case I added a x and a y first and then a z and got this vector, it does not matter in which order you add these vectors, because we have already proved that addition of vectors is commutative. So, I could have added a y and a z first and then added a x, I will still end up with the same vector a. So, now the meaning is quite clear. When I write a equals a x I plus a y j plus a z k, I am writing a vector a x times I pointing in x direction, a vector a y times j of magnitude a y pointing in y direction, and a vector of magnitude a z pointing in k direction, and adding them all up, and that is the vector a. A x is called the x component of a, and a y the y component, a z the z component. So, let us see, suppose I have write a vector v is equal to I plus 2 j plus let us say 3 k. How would it look? X, y, z. So, I would make the vector I unit vector in this direction plus 2 j would be a vector of magnitude 2 in this direction. So, this would be I plus 2 j, and 3 k would be of magnitude 3 in this direction. So, up to this point, let us make this vector here, this then summation of all 3, this vector would be I plus 2 j plus 3 k. How about the magnitude of this vector? You can see that I can first add these two, get the magnitude of this, that would be a x square plus a y square square root, and then again add a perpendicular vector to it, which will be a z. So, the net magnitude would be square root of this component, which is a x square plus a y square, and then a perpendicular component a z, add them all up and take the square root. This is the magnitude of the vector, and you can see that direction is easily seen and visualized by making the vector using these unit vectors. Having written a vector in its algebraic form, let us ask, how do I add two vectors? Suppose there is another vector b, which is b x I plus b y j plus b z k. When I add the two vectors a plus b, you can see graphically and carry it out that the net vector would have a x component which is the summation of the x components of individual vectors. Then I add the y components of individual vectors and then the z components of the individual vectors. Similarly, minus b would be nothing but each component of the b vector would become negative. And therefore, a minus b, which is nothing but adding a and minus b, would be same as a x minus b x I plus a y minus b y j plus a z minus b z. Okay. Having written the vectors a y j plus a z k and b as b x I plus b y j plus b z k, we are now ready to write their products. All possible combinations of the products are a x times b x, a x times b y, a x times b z, similarly a y times b x, a y times b y, a y times b z, and a z times b x, a z times b y, and a z times b z. These are all possible products of different components of the two vectors, out of which ones do we take? Which ones do we define as vectors and scalars is the next task that we are going to address. You already know from your intermediate 12th grade that there are two kinds of products: a dot product, which is a scalar product, which is given as the sum of a x b x plus a y b y plus a z b z, and the cross product a cross b, which is a vector quantity, which is given as a component a y b z minus a z b y in x direction plus j a z b x minus a x b z in y direction plus k, the component in z direction is a x b y minus a y b x. But as I showed you on the last slide, there are these all possible products which are being taken here, but why do we take them in this particular combination? Why do I define this to be a scalar product? Why do I define this to be a vector product is the question that I want to address now, so that we get a better understanding as to why the products of these two vectors are defined in such a manner. And for that, I want to look at another property of vector quantities, and that is the change of vector components under rotation. So far we have just looked at a vector quantity as something that has a direction and that has a magnitude, but now we are going to look at some more properties, and one property that we specifically look at is the change of vector components under rotation. Let us see that. Suppose you have a friend who asks you how far is the house of another friend, and you say it is 500 meters, or you say you walk 300 meters to the east, I am just taking the previous example, and 400 meters to the north, so that the direct distance of that house is 500 meters, but you have to walk in a zigzag manner, in that you have to go east first and then north. Total distance you cover is 700 meters. Now, suppose you have another friend who is looking at it from a different frame. So, for the previous friend you had the x axis along the east and y axis along the north, but another friend has his axis x prime, and this at some angle theta from the east and y prime at some angle theta from the north. Although the distance travelled by this person in going to the other house is going to be 700 meters in both the frames. However, this vector you can see is going to have components which are not going to be 300 and 400 meters, but this is going to be its x component and this is going to be its y component. So, although the vector remains the same, it is 500 meters in this northeast direction, but its components along different frames are different. On the other hand, for the scalar quantity distance, that remains the same, unchanged. So, what we conclude, a scalar quantity which is nothing but a number remains unchanged in the two frames. On the other hand, we also see that the components of a vector quantity change when we go from one frame, say x y, to another frame which is rotated with respect to the first frame, x prime y prime, which is rotated by an angle theta with respect to the first frame. For the same vector quantity which in space is still pointing in the same direction, has the same magnitude, this is going to be x component, this is going to be y component. On the other hand, the x prime component is going to be this and y prime component is going to be this. And the relationship between x prime and y prime component and x and y component is well known, and that is what we are going to derive now. So, a vector quantity must follow that relationship, its components should change according to that relationship when we go from one frame to another frame which is rotated with respect to the first frame. So, let us derive the relationship. So, let us say there is a vector pointing in a certain direction in the original frame x and y, so that its this is its x component and this is its y component. I am looking at the same vector from another frame, and let me now use a different color. X prime and y prime frame, which is rotated with respect to the first frame by an angle theta. The component x prime is going to be given here. This is going to be x prime and this is going to be y prime. You can also see that this angle is also theta. So, now we want to find, let me also draw a perpendicular from here to here, this angle is also theta. Let this point be A, B, C, this is the origin. Let this point be B prime, let this point be C prime. So, we see that x prime component is going to be equal to O C prime plus C prime B prime, that is this plus this. And let me also call this point where it intersects as D. OC prime is nothing but x cosine theta. So, this is going to be x cosine of theta plus C prime B prime is nothing but C prime D plus D B prime. So, this is nothing but C prime D plus D B prime, which is equal to x cosine of theta. C prime D is nothing but D B sine of theta, D B sine of theta. I am deliberately writing it like this, plus D B prime is nothing but A D sine of theta. Sine of theta I have taken out. Now, you see D B plus A D is nothing but y. So, I can write this as x cosine of theta plus y sine of theta. And what I have shown you in the previous page is that x prime is x cosine of theta plus y sine of theta. Similarly, if I were to calculate y prime, this length, this, let me extend this here, this distance is nothing but, this angle is theta, y cosine of theta minus this distance, which is the same as this distance, which is nothing but x sine theta. So, y prime therefore, is going to be y cosine of theta minus x sine of theta, and this is how the x and y components of the vector are going to change. I wrote this for a displacement vector x and y, but in general you can do the same exercise and you would find that if I look at a vector A in the two frames, which are rotated with respect to each other, then A x prime, that is the component of A in the rotated frame, is going to be equal to A x cosine of theta plus A y sine of theta, and A y prime is going to be equal to minus A x sine of theta plus A y cosine of theta. This is how the components of a vector transform. On the other hand, the scalar number remains the same number in both the frames. We have looked at, in this case, when we rotated the frame about the z axis, because only x prime and y prime axis changed. We can do the same thing for other axes also. So, for example, suppose we rotate about the x axis. So, let us say we have x, which is coming out, y and z, and suppose we take the new frame by rotating about the x axis, x y and z x is the same. So, this is going to be y prime and this is going to be z prime by an angle theta. Then you can see that what we did earlier, by that A y prime in the rotated frame, when I rotate about the x axis, is going to be A y cosine of theta plus A z sine of theta, and A z prime is going to be equal to minus A z sine of theta, or minus A y sine of theta plus A z cosine of theta. Similarly, if I rotate about the y axis, let us do that. If I rotate about the y axis, this is going to be x axis, z axis, y axis coming out, and make my new z prime and x prime axis like this. By rotating about the y axis, you will see that a z prime is going to be a z cosine of theta plus a y sine of theta, and a x prime is going to be minus a z sine of theta plus a y cosine of theta. So, this is how the vector components of a vector transform under rotation with respect to x axis, y axis or z axis. That is, if I rotate about the z axis, I change x prime and y prime components. If I rotate about the x axis, I change y and z components, and if I rotate about the y axis, I change x and z components, and they change in a very, very specific manner. On the other hand, the scalar quantity remains unchanged even if it is looked at from a rotated frame, and that we are going to use now to define our products. So, first quantity I told you about is of those, let me write all the components ax, bx, ax, by, ax, bz, ay, bx, ay, by, ay, bz, az, bx, az, by, az, bz. Of all these 9 components, we took 3 of them and wrote a scalar product as the sum of ax bx plus ay by plus az bz, and we call this a scalar product. That is, if I take these components and add them up, this gives me a number which is scalar. How do I prove it? I prove it by going to a new frame in which the scalar product is going to be ax prime bx prime plus ay prime by prime plus az prime bz prime, and this ax bx plus ay by plus az bz must be the same as ax prime bx prime plus ay prime by prime plus az prime bz prime if this is a scalar. Let us show that for one specific case, and rest I will leave for you as an exercise. So, let us look at the rotation about z axis. So, that in that case ax prime would be equal to ax cosine theta plus ay sine theta, bx prime would be similarly bx cosine theta plus by sine theta, ay prime would be minus ax sine theta plus ay cosine theta, by prime would be equal to minus bx sine theta plus by cosine of theta. A z prime would be same as az, because z axis is not changing, I am rotating about the z axis. Bz prime would be same as bz. Now, let us calculate ax prime bx prime plus ay prime by prime plus az prime bz prime, and this would come out to be equal to ax cosine theta plus ay sine theta times bx cosine theta plus by sin theta plus minus a x sin theta plus a y cosine theta times minus b x sin theta plus b y cosine theta plus a z times b z. This gives you a x times b x cosine square theta plus a y times b y sin square theta. The first term gives you a x b x cosine square theta plus a x b y cosine theta sin theta plus a y b x cosine theta sin theta plus a y b y sin square theta plus a x b x sin square theta minus a x b y cosine theta sin theta minus a y b x cosine theta sin theta plus a y b y cosine square theta plus a z b z. Now, you see this term cancels with this term cancels with this, and a x b x cosine square theta plus a x b x sin square theta gives me a x b x. Similarly, a y b y sin square theta plus a y b y cosine square theta gives me a y b y plus last term is a z b z. So, what I showed you just now by transforming the different components, that a x prime b x prime plus a y prime b y prime plus a z prime b z prime, even under transformation remains the same as a x b x plus a y b y plus a z b z, and therefore, this is a scalar quantity, and that is precisely why we take this particular combination a x b x plus a y b y plus a z b z and call this a scalar product. Similarly, the other quantity that we define is the vector product, in which case A cross B is given as I, the x component is given as a y b z minus a z b y, plus the y component is given as a z b x minus a x b z, plus the z component is given as a x b y minus a y b x. What happens under transformation? Under transformation, if I transform each component a x, a y, b y the way we did earlier, these components should also mix according to the rule of vector transformation. And I leave it as an exercise to show that A cross B, if I take its component in x prime direction, it is equal to A cross B x component cosine of theta plus A cross B is y component sine of theta. Similarly, A cross B y prime component, if I am rotating, if I am changing only x prime and y prime axis and by rotation about the z axis, should be equal to minus A cross B, the x component of sine theta, plus A cross B, y component cosine of theta. I leave this as an exercise for you. So, it is this combination a x b y minus b y a x and things like those that defines the vector product for us. So, product of two vectors one is a scalar product which is a written as a dot b, which is nothing but a x b x plus a y b y plus a z b z, and the other is the vector product which gives me a vector quantity which in a short term I can write as a determinant I j k a x a y a z b x b y b z, a determinant of this, and this is a cross b. I leave it for you to check that this gives the same expression as we used earlier.